Okay, so the last few days we have been talking about different mole conversions. We already learned the mole conversion that goes from moles to atoms. We talked about the mole conversion that goes from moles to grams, and today we're going to learn one that goes from moles to volume. Okay, now when we're doing the mole to volume, it's very important that you understand that we can only do this with gases. Okay, so gases have a very important trait that allows their volume to be very predictable. Okay, what that means is if somebody is back there and sprays some perfume, okay, if Abby back there decides to spray some perfume, eventually up here, am I going to smell it?
Yes.
Yes, because gases will expand to fill the container they are in, correct? Which is why if you were to do the same thing outside, would I smell it quite as fast? No, because outside is a much bigger container to expand to fill, right? So, gases have a very unique characteristic. When they have equal volumes at the same temperature and pressure, they will also contain an equal number of particles or moles or atoms or molecules or whatever you want to place in there when we're talking about Avogadro's number. Okay, when we're also talking about volume, we need to take into account this new concept called standard temperature and pressure. We're going to talk about it a little bit right now, but it's not really going to come into play for a few units. But standard temperature and pressure, which is shorthand STP, is when we are talking about 0 degrees Celsius, which is when water freezes, and 1 atmosphere, which is sea level. So are we at 1 atmosphere here? No. Okay. All right. If we are at standard temperature and pressure, if. Everyone hear that? If we are at standard temperature and pressure, 1 mole of any gas is going to occupy 22.4 liters of volume. Any gas. Doesn't matter. All right, so is this going to be a conversion factor that we have to figure out every time, like molar mass, or that stays the same every time, like Avogadro's number? It stays the same every time. As long as you have a gas, and as long as it's under STP, the conversion factor is never going to change. So, let's do an example. So, number 13. At STP, what volume does 0.335 moles of C2H6 occupy? Okay, so the first step is to, first of all, figure out what conversion factor we need. So do we have a conversion factor that allows us to go from moles to volume? Yes, what is it? 1 mole equals 22.4 liters. Okay, now I get to start my conversion. In every conversion problem, I always write down what I am given in the problem, right? So I'm going to start off with this guy right here. So 0.335 moles of C2H6. Where are we going? Volume, which is liters. So now I need a conversion factor. I need to put what I want over what I have. What unit do I want to convert to? Liters. So am I going to use the left side or the right side of my conversion factor? Right side. So 22.4 liters. What goes on the bottom? The 1 mole. Again, once you start to use one conversion factor, you have to use the whole thing. This unit cancels out that unit. We're left with liters, which is what we wanted. So now all we have to do is plug it into our calculator. So if we do 0.335 times 22.4, we get an answer of 7.504. How many significant figures do I get to keep? 3, because 0.335 has 3. So I get to round to this spot right here. So what's my answer going to be? 7.50. What's my unit? Liters of C2H6. Is it very important that I put that 0 right there? Yes. Why? That's telling you that my number has been rounded to the hundredths place, right? So that's telling you my answer is anywhere in the range from 7.45 7.95 to 7.504, right? That's my range. That's a lot more exact than 7.45 to 7.54, correct? All right, so that 0 is very, very important. All right, let's do another example. Okay, this one says, determine the volume in liters of 0.60 moles of SO2 gas at STP. Am I going to use the same conversion factor this time around? Yes, because I need to go from moles to liters. What is my first step in any conversion? Write down what you're converting. So we're converting 0.60 moles of SO2. Now what do I do? We need to go where? Liters. So I need my conversion factor. What goes on top? Liters. So the left or the right side of my conversion factor? Right? What goes on the bottom? 1 mole. Okay, that cancels out. That we are left with liters. Is that what we want? Yes. So now all we have to do is the math. We do 0.6 times 22.4, and we get 13.44. How many significant figures do I get to keep? 2, because 0.60 only has 2, so I'm going to round this to 13. What's my unit? Liters SO2. This pattern has been the same for every single conversion, right? All right. Now, we're going to switch gears just a little bit. The next thing we're going to do is not exactly a conversion, but it involves a conversion factor, which is a little bit of a different process. Okay, this time we're going to talk about molar mass and we're going to compare it to density. So again, if we are still talking about gases, this only works for gases. Gases will sink or float based on the density of the gas. If the gas is less dense, it'll float, which is why helium balloons float at birthday parties. If it is less dense, it'll fall. Okay, also, temperature can affect it. Okay, this is why hot air balloons, they usually have a heater that heats the gas up. As the gas gets heated up, it causes the balloon to rise. When they're at the altitude they want, they turn the heater off so that it will kind of stabilize with the air around it. When it's at the same temperature, it'll kind of float. All right, so density, if you guys remember, is grams per liter. Okay, and this will change if you change temperature. So if the gas is at standard temperature and pressure, so if we're at 0 degrees Celsius, if we're at 1 atmosphere, then we can compare 1 mole of a gas to its density. Okay, why is this important? Because think about what's around us. Carbon dioxide is around us. Oxygen is around us. Carbon monoxide is around us. All these gases are around us, but we can't see them. We can't really study them unless we just have to study what's around them. So if we can figure out the molar mass of a gas, we can then use the periodic table to determine the gas, right? So basically, this isn't exactly a conversion. It's like a roundabout way. We're trying to solve for something we can't see. All right, so let's do an example. Sorry. All right, so let's do an example. And again, like I said, this is not a conversion. Okay, we're going to use a conversion factor, but this is not a conversion. All right, number 15. The density of a gaseous compound containing carbon and oxygen is found to be 1.964 grams per liter at STP. What is the molar mass of the compound? Well, let's see what we have. First of all, we know that our density is 1.964 grams per liter. So in 1 liter, we're going to have 1.964 grams. We also know that 1 mole of this gas is going to equal 22.4 liters. And we also know that molar mass has to be in the unit of grams per mole. So we are currently in grams per liter, and we want to be in grams per mole. Right? We're in grams per liter, we want grams per mole. .964. I ran out of room. All right, so what you do to solve this problem is you do 1.964 We're going to write down what was given to us in the problem. Grams. And we have it written like this, correct? What does this actually mean when it's on the bottom of a slash? Grams per liter. It's technically the denominator, right? So instead of writing it like that, we're going to write it just a little bit differently. We're going to write it like this. Is that not saying the exact same thing? Yes. So see what I mean? How it's not exactly the same type of conversion we've been doing. It's a little bit different. So now we have to think to ourselves. We want grams per mole, and we are in grams per liters, correct? So we need to go from grams to liters to grams to moles. So do I need my grams to cancel out? No. I want my grams to stay the same, correct? What do I need to get rid of? Liters. So I need a conversion factor that has liters on the top. What needs to be on the bottom? Moles. So do we have a conversion factor that is liters and moles? What goes in front of the liters? What goes in front of the moles? 1 mole. Okay? Our liters cancels out. We're left with grams over moles. Is that the unit we want? Yes. So then we are ready to do the math. So if we do 1.964 times 22.4, we get 43.9936. Now I need to count my significant figures, right? How many are right here? 4. So how many do I get to keep? Now I've had this question asked several times today. Ms. Tackett, why are we only looking at that first number? Why are we not looking at our conversion factor? Well, there's actually 2 answers. First of all, the density was the only number given to us in the problem, right? So that's the only thing we're looking off of. Secondly, 22.4 is a conversion factor, which is a constant, which is a standard. Those don't affect your significant figures. So either way you look at it, the only one that's going to affect our significant figures is the 1.964. So basically, those are going to go away, and our answer is going to be 43.99 grams per mole. Now, if you remember, this was a combination of carbon and oxygen, right? Now, if this was dual credit chem, aka those of you who are taking it next year, we would figure out what gas molecule we are, but we're just going to stop there. Okay, we'd have to do a lot more math. We don't want to do that, right? All right, so I think you guys are ready for some practice. So the first 2 problems, number 16 and number 17, are just mole conversions using the new conversion factor we used. Number 18 is a density problem. Okay, you have 20 minutes to do this in class. Why would I give you 20 minutes? So you can ask questions and make sure you understand it before you leave. Don't forget about your homework quiz tomorrow. Okay?